Let's say you've got a particularly nasty function that looks something like this one, and you're asked to find the derivative. How would you do it? Well, you'd probably start with the quotient rule, and then you'd have to use the product rule for the numerator and the chain rule for the denominator, and it would be kind of tedious. You'd have to keep track of a lot of things. Well, it'd be possible, but it wouldn't be very fun. So I'm going to teach you something called logarithmic differentiation, which makes finding the derivative of complicated functions much easier. And it uses the properties of logs to remove the products and quotients from properties or from functions like this. So, in case you've forgotten, we can review the log properties. So if we have the natural log of a times b, that's the same thing as the natural log of a plus the natural log of b. And the same thing for division, a over b is going to be the natural log of a minus the natural log of b. And then there's one more. The natural log of a to the b power is going to be b times the natural log of a. And the reason we use the natural log in this case is because if we have the natural log of x, then the derivative of that is going to be 1 over x, which is nice and pretty for us. These log properties, of course, work for any base, but for logarithmic differentiation we stick to the natural logs. So the first thing we want to do in this problem is take the natural log of both sides so that we can simplify it using the log properties. So if you take natural log of f of x, that'll become the natural log of 5x sine 4x over square root of cosine of x. So we can't really do much with the left side, so that will stay the same for now. But then we've got this quotient here that we can get rid of with this property. So we take the natural log of the numerator minus the natural log of the denominator. And we're not quite done yet, because now we've got these products inside a natural log, and this right here, this square root of cosine x, is the same thing as cosine x to the 1/2 power. So we can actually use this rule right here to simplify that even further. So if I write this out, I'm going to go ahead and split this up into all its components using this property right here. And then we're going to subtract this, we're going to bring the 1/2 to the outside, and then we're just going to multiply by the natural log of cosine of x. So that looks a little more approachable, and now we're ready to find the derivative. So we use implicit differentiation, and we start with this left side here, the natural log of f of x. What's the derivative of that? Well, that's going to be the 1 over f of x. But this is a compound function, so you have to multiply by the derivative of the inside. And the derivative of f of x is f prime of x, which is, of course, what we're looking for here. And so then we take the derivative of this other side. I'm going to erase that. The first thing is natural log of 5, which is just a constant, so that's 0, plus the natural log of x, which is 1 over x, plus, and now we're getting a little bit trickier. This is a compound function, so we start with the derivative of the outside, 1 over sine 4x, and then we multiply by the derivative of the inside. But the derivative of the inside is also tricky, because it's also a compound function with a 4x in there, so we've got to multiply by the derivative of that inside, which is just 4. And then we've got one final term, this 1/2 natural log of cosine x. So then 1/2 stays there. And then we take the derivative of the natural log of cosine x, which is also a compound function. So we have to multiply by the derivative of the inside, which is just sine x. So hopefully you got all that. It's not too bad. All of those terms are just separated by pluses and minuses. Notice I didn't have to do any product rules, or, well, I guess you could call that a product rule, but it's just a constant, so that's not so bad. And there was no division either, so basically I didn't have to think a whole lot when I did that. But we're not quite done yet, because we can simplify this even more. The first thing I want to get rid of is this 1 over f of x, because it's on the wrong side of the equation, because I want the f prime of x to be all alone. So I'm going to go ahead and multiply both sides by f of x, and then I'm going to do a little bit of simplifying to this stuff right here. So 1 over x is pretty simple, but we've got a cosine over a sine, which is secretly just cotangent of 4x. So I'm going to add, and then there's this 4 right here, so 4 times cotangent 4x. And then we've got a subtraction right here, but notice this is actually a double negative because we're subtracting a negative, so that becomes a positive. And then we've got a sine over cosine, which is actually just tangent, so 1/2 tangent x. And then we're not quite done yet, because we've got one last detail to look at, this f of x right here. What is f of x? Well, it's exactly what we started with, right here. So without even thinking, all I have to do is put in what f of x equals. 5x sine 4x over square root cosine x. And then we multiply that by what we just found. 4 cotangent 4x 1/2 tangent x. And then you found the derivative. And of course it doesn't look very pretty. In fact, it would look a lot prettier if you found it using the quotient rule, but they are equivalent derivatives, and this one is certainly much easier to find. The only thing I had to do was a bunch of simplifying, which is really kind of fun if you enjoy that sort of thing. And it's not terribly difficult to do. You don't have to think about it too much, you just have to make sure you know what to look for. Whereas if you were to use the quotient rule, you'd be keeping track of a whole bunch of highs and lows and v's and u's and u primes and v primes. So that's just a whole mess. And if all you're looking for is the derivative at certain points, then this is a much faster method to use for complicated functions like this.